Hello everyone, and this video I'm going to demonstrate an energy conservation problem. Okay, and for the energy conservation problem, the problem is here. So in this problem, I think we demonstrate a similar problem in chapter 5, and that time we use a Newton's second law. Newton's second law. Okay, but in this time we'll use energy conservation to solve this problem. You say you apply external force on this object, okay, and this force has angle theta with respect to the horizontal direction, and then you apply this force because you apply a force on object, so the object will have the acceleration will have velocity change, and so you are moving to the right. Okay, and it's moving on rough surface. Okay, so it also has a friction. And the problem asks what is the optimum angle theta? Okay, and which can let you have the largest possible velocity after the block has moved 3.0 meter to the right. Okay, what's the optimum angle theta? And if you if for you want to have maximum velocity after the object moving 3.0 meter to the right. Okay, so in this problem, yeah, we will use the energy conservation to solve problem, and there's more setup of this problem. So initially, this object is at rest. Okay, and the mass of this object, let's call it m, and the force, the magnitude of force, we just simply give it a for f. Okay, let's make life easier. Okay, so let's start with the energy conservation calculation. So energy conservation, it's really simple. Delta K plus delta U equal to heat plus work done by the external force. And okay. So for such energy conservation calculation, we need to know initial state and final state. What's the kinetic energy and potential energy for the initial state and final state? Okay. So let's start with initial state. Initially, this object is at rest, so there's no velocity. No velocity. That means you don't have the kinetic energy. And what's the potential energy at initial state? In this problem, okay, in this course, in this semester, we only have two kinds of potential energy. One is elastic potential energy or spring force potential energy. Okay, the other is gravitational potential energy. Okay, for this problem, we just assume it's moving a horizontal direction, so there won't be a height changes. So the potential energy change must be zero. Okay, so and it's moving on the same horizontal level, so the potential energy we can just treat it as zero. And there is no spring in the system, so elastic potential energy also zero. Okay, so initial state potential energy also zero. Okay, for the final state with moving to the 3 meter to the right, it still carries some velocity, right? I call it VF. So we have the velocity VF and the square. And what's the potential energy? Well, because it's moving horizontally, so let's just assume its potential energy also zero. Okay, there's no height difference. Okay, it's moving at the same height. So just set this height, this height as the origin. So the potential energy is zero. Okay, so let's for kinetic energy and potential energy. Okay, so right now the biggest part is the big problem is in this uh, typical part in this problem is how to evaluate the Q and work Q heat and the work done by external force. And in this, I think in this section, we always say the heat is generated by the friction. Okay, heat is generated by friction. Okay, so heat is generated by heat, the friction. Heat And I keep saying that because it's release the heat, so there will be a negative sign in front of the heat, the friction, the work done by the friction force. So there will be a negative, and it's friction force times the distance. Okay, the distance is 3 meters. Okay, so let's write down minus Fk times 3 meter. And the work done by external force, okay, let's see, because in this problem you have external force here, okay? And what's the work done by this external force? Okay, the work, you understand the work is F dot delta R. Okay, so that means the force is parallel to the moving direction, only do the work. Okay, the force parallel to the moving direction, do the work. So for this problem, only F cosine theta do the work. Okay, you must understand only F cosine theta do the work. Only F cosine theta do the work. And how long is travel for this problem? It is 3 meters, so it's times 3. And it's positive. Why? Because, like I said, because positive means you add energy into your system. So the pulling force, yeah, you're pulling this object. That means you are adding the energy into your little system, and that make the object move. Okay, that has a velocity change. That because you add the energy into your system. So that means the work is positive. The work done by external force is positive. And only the force that's parallel to the moving direction does the work. So you only have F cosine theta do the work. Okay, so it's not F times 3. Okay, be careful. Okay, so we all have all the information, so we can put everything into the energy conservation equation. So what we have now, what we will get, let me see. Okay, so let's see, Kf minus Ki plus Uf minus Ui equals to Q plus W external force. So the final initial state, kinetic energy final state minus initial state. So it's 1 over 2 mvf squared. And the potential energy difference, yes, over 0. So that's a 0, very good. And Q is minus Fk times 3. And the work done by external force is positive F times cosine theta and times 3. Okay. And in this problem, yeah, that's only another difficult problem is what is Fk? Can we find the Fk? So this will back to the force analysis of this problem. Okay, let me draw the free body diagram of this object. Maybe it's very rough, but maybe it's very rough. Okay, so the force here and this theta, and you have normal force, and we have the gravitational force. Okay, and friction coefficient here. Does this problem give you friction coefficient? Let me check. So this problem gives a friction coefficient. Let me write down here. Friction coefficient is 0.15. 0.15. Okay, so the friction force, we all know that in previous section on Newton's second law, the friction force probably is proportional to your normal force, and there's a kinetic friction coefficient. And this problem give you a new K. So that's part question is how to get the normal force. Okay, the normal force here we have to do the force analysis because this object is moving along x direction. So let's know the object doesn't move in y direction. Okay, it only move on x direction. So in this system, the y direction, does not have an acceleration. Right direction doesn't have an acceleration. Acceleration. So this can give you useless Newton's second law. Summation Fy equal to MAY. Only care about the y direction right now. And there's no acceleration in y direction. That means your sigma Fy is equal to 0. Okay, sigma Fy is 0. Okay, we can be some. Okay, so let's also assume there's a positive direction, upwards positive direction. So we'll have m plus f sine theta minus mg equal to 0. Okay, so and then we'll have normal force, right? The normal force is equal to mg minus f sine theta. Okay, so we found the normal force. And then we can put this normal force is into the fk. So why we need this? Okay, you understand. Okay. Let's see. Okay. Okay. Should I change color? MVF squared equal to minus nu k times n. So it's ng minus f sine theta. So okay, and times 3 and plus f times cosine theta times 3. Okay. So so we finally has these equations. Okay, so and the reason why we might have to replace the normal force because we want to replace the m by the information we have known. Okay, because f is the problem setup, m is the problem setup, and theta is a problem setup. We have to change the n to the information we have known. Okay, that's why we have to replace the n. And can we solve this by? Okay, we reach a very complicated equation. That's really true. We reach a very complicated equation, and so you can see. But there's two ways to solve this problem. The one way is okay, you do algebra work, and you express your VF. Final velocity is a VF function of theta, and then the problem is find optimum angle theta for the maximum VF. So if you do and you do a derivative, find out extreme value of the function. You know that. Okay. And then you will find the theta is da 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 da. Okay, but you already know that if you do algebra work, VF will be a very complicated function of theta. This will make the problem much difficult to solve. We just do a little trick, circumvent this difficulty. We just use the whole term, the kinetic energy. Use this kinetic energy as the major function. So we just call it Kf. Okay, and Kf is a function of theta, right? Kf function of theta. Okay, if we find the optimum theta for the maximum kinetic energy, because kinetic energy is related to velocity, closely related to velocity. Maximum kinetic energy, maximum velocity. Okay, and it's much easier to solve. Okay, so let's start it. Okay, we use the kinetic energy as a function and do a derivative with respect to theta. So the first term will kick out because the first term is minus nu k ng, and it's not function of theta, so it becomes 0. The second term is nu kf, and the sine derivative to theta will become cosine. Hmm. And it's 3, right? The first term derivative is 3. Okay. The second term is also 3. And it's minus sine theta. And then if the derivative equal to 0, you will find an extreme value equal to, let's say, the fund derivative or the theta equal to 0, you will find extreme value. And if this is a 0, so we can divide it by 3, divided by f. Okay. Oh, everything becomes so simple. So you will have the mu k cosine theta plus minus sine theta equal to 0. So you have nu k equal to tangent theta. So theta will be arctangent nu k. Okay, so the problem given nu k is 0.15. So the theta is, I think 8 point something. Remember in class, someone calculates 8 point something. Uh-huh. Yeah, 8.53 degree. Okay, 8.53 degree. Okay, so 8.53 degree, you have a maximum velocity after the object moving 3 meter to the right. Okay, but why there's but why there is optimum set for this? Because you might think if I pull the object horizontally, complete horizontally, it should have the maximum velocity because the work I do the work good because my applied force is totally parallel to the moving direction. That should be have maximum work. And the maximum work on this option, there should be a maximum velocity after all. But the problem why there's optimum because you need if in because it's a normal force in a friction. Okay, because you see the normal force. Okay, normal force equals mg minus f sine theta. So you need some theta value, okay, to reduce the normal force. A little theta value to reduce the normal force. Reduce the normal force, you will also reduce the friction, okay? But after all, you cannot have very large value of theta, okay? Okay, if you have very large value of theta, like as I say, your component that does the work will become very few, okay? Because if equal to f cosine theta. If theta is very large and you have very small component in f cosine theta, and you have a small f cosine theta, you cannot keep the maximum velocity. But you still need some velocity to reduce the normal force, to reduce the friction. So there will be an optimum value of the theta. Okay, so if your system has friction, okay, so you need a little theta to make sure you have maximum velocity. Okay, not parallel. Okay, so that's friction. So friction is sometimes very annoying. Okay, but friction is the real world. Friction is everywhere. Okay. Okay, so this problem is more realistic. Okay. And finally, we didn't do a derivative on the velocity directly because yeah, you can do algebra work. The velocity is very complicated function of theta. But we use the kinetic energy after all. Instead, we use kinetic energy because it's much easier to do the calculation. Okay, hopefully you can get more understanding on energy conservation problem. So using energy conservation is much easier than the Newton's second law of motion. Okay. And that's also the reason we love energy conservation. Okay, that's we make the problem solving the problem much easier. Okay, Newton's second law, yeah, it's very complicated. I know. Okay, so this is the problem. So I will stop the video here. So maybe I just stop here. Okay. Okay, see you in next video. Bye bye. Bye bye. Oh, oh, oh. Ooh.